That might be easier.
Okay, sure.
Yeah, it absolutely will be.
All right, last lecture for today. So we have the second lecture about the AI.
Okay, so yesterday we touched how the signals are produced by the detector and how, in principle, AI can help in let's say, reducing this data or manipulating this data. Today we'll see the part related specifically to the AI, just really the basic. Okay, now it's working. So the basic idea behind the neural network and behind how AI works. With a couple of examples. In particular, there will be one, since we had the discussion yesterday with some of you, and I think that will be interesting to touch this, even if it's not directly related to this low-level data reduction, but still interesting to show, let's say, the possibility that AI may offer in tackling some problems that traditionally are difficult to be solved. And then we'll finish with the autoencoder that will be the subject for tomorrow, that is, focused on putting together. So you have the signal, you have your AI algorithms, how to manipulate data, you put together and try to see what can come out from the combination of it. Okay, so I highlighted names, so sorry again for people that are already experts. Sorry, I try really from the basic things, the basic concept, and I try all the time to highlight and the words that are usually used, the term usually used in AI world. I mean, from data scientists, and at the end you get used to keep names that are, just a simple one-to-one translation of what we are used to deal with. It's not different, but just they use it in a different way. For instance, I don't know, epoch, what is an epoch? You go through your data set once, and this is called epoch. Or data set. Data set is usually a combination of independent and dependent variables that you have, and you have a model, something that in some way connect the variables with some parameters. And the other important, let's say, part of the AI is what's called the loss or the cost function. So something that allows you to change the parameters to obtain what you want. I mean, some way you want to connect X and Y, the independent to the dependent variables, and you have something to check if what you are expecting, the guess you are doing, is correct with respect to E. So how it works? You have your data set that usually is large enough to be split in different chunks. So you get at least two of them. Usually you use three. Actually, in the example, we'll see that we are going to use three of them, but in principle, only two are enough. You divided them in a subsection, subpart, a subset that's called the training set, and you have another part that is called the test set. That is the one where you are expecting to make prediction. So you train your system, your algorithms on the training part, and you check the results on the test part. During the training, you may also use it to avoid what is called the overtraining that is reported here. For instance, if I have this collection of points, I can complicate my model. In this case, it's just a fit. So I have a function that needs to go through dots. Who knows which one is the correct one? I mean, nobody knows, but you can try, with different polynomials. This is just the first order, this is the second, and then you go higher and higher and higher, and you at some point with the degree 20, you really go through all points. But is it what we want? I mean, we really want to go through all points? Probably not, because if I now add a new point to this data set, my function is not going to be correctly taking this data. So we have to be very careful in the model you have, the way how you train it to avoid that the model goes exactly on the training data set, but is not has no any predictive power for the remaining part of your data set. It is called the test data set. Another so important part is that obviously you are expecting that your model or your algorithms is learning from the training set and can be applied to the test. One important part that I'm gonna touch many times in this talk is about the fitting is not predicting. So there are two different things. Fitting means that you are, happy if you can reproduce what you have. Predicting is a little bit more. You are trying to pin down the underlying law and expecting to be able to extend the range where this application works. Maybe within the same domain of your data points or extending the domain. Again, there are some philosophical, let's say, consideration that is is not obvious, and nobody can really tell you if the machine learning algorithm is gonna really pin down the underlying law. It may be possible to just it's very good to mimic and reproduce your training data, may reproduce very well your test data, but nothing guaranteed that if you add another point, it's gonna get also this point good. Okay. And there is also, some ideas or some consideration about the complexity of the model we see. They call it expressivity. So more complicated is the model. In principle, again, if you look at the polynomial fit of this function, obviously more degrees you add, easier is the way that your curve goes through all points. So same thing, just the thing big, and if you multiply in a multidimensional space with the features that are not necessarily points, and maybe other features of your data set, is the same thing. More parameters you add to your fitting function, generalized fitting function, easier is the way that you can get correctly the data you are starting from. But again, doesn't mean that you end up with a good predictivity, let's say, for the model. And on top of that, there is another issue that yesterday I already mentioned, that the so-called no free lunch theory, that is there is no receipt. I mean, you are not guaranteed that the model you are using is the right one, and say that all models are wrong, but some of them can be useful. This is really the summary of this approach, that you never know if the neural nets that you are writing is the perfect one or is completely wrong, just usable in that range. And nobody can tell you. I mean, this is mathematically proved, so it's a kind of limit for the AI that tells you that there are. I mean, the only way to check if the results are good or bad is cross validation. So you have to use your model in different situations, in different configuration, and hope that the one that you have. I mean, based on the large data set, allows you to really use it and give a good prediction. And this is also the reason why there are some ethical problems, for instance, driving the car automatically in an autonomous way, because there is no guarantee that the algorithm cannot do something bad. Okay, so this is, if you think about this kind of sparing or complicated issue, because with a human being, you can always blame a human being for a machine, and it's very difficult to blame a machine. So, and this poses problems. This really pose problems, for instance, in the nuclear industry. AI is not so largely used exactly for this reason, because the risk of a failure is so, dramatic in terms of consequences, that even if the method probably works much better than the traditional one, still the AI is not as diffuse as you may think. I mean, you may imagine. So in this area where there are big risks connected to the output of the AI algorithms, there are still resistance, and there are ethical issues again that are not so clear how to deal with. Anyway, so I mean, this is just to say that the data science is not, let's say, an exact science, and the competence and also the background, the experience of the data scientists that shape the algorithms, that shape the, put the model together and decide which one is better than the other is at the end is the winning part of as usual, the human part is fundamental also in AI at the end of the day. Okay, so how it works, how the machine learning can learn from your data. Again, you have this data set that is made by, they call it examples. So this is just a list, let's say, of numbers or whatever features you can consider, images, whatever this is the reason why, we think in terms of numbers mainly, but in principle, AI can fit images of animals. So, I mean, obviously, it's not strictly a number. So they call it examples, and they say that, examples are a collection of features. Features are the characteristics. In our case, it's quite simple. For instance, example can be data entries, an event in a reaction, in a scattering, and features are the form momenta of particles. This is, what you, at the end of the day, what you are trying to fit, what you are trying to extract, what you are trying to manipulate. The data then is divided in batches. So usually you don't use the entire data set because data sets are big. So you use small part, and then you use this chunk and train or use part of it to train your algorithms. And then you go through the algorithm many times. Why that? Because you start usually from the weight that we were discussing before. We see in a more tailored way, next slide, about the linear regression, but in principle, so you're starting from a model that has parameters completely, random chosen. And you want to, at the end of the day, come up with a model that, let's say, is fitting perfectly my function. So if I start, in a totally random way, I can go through my points once, and then it means that my weights gets adjusted, and then go again. And then I'm moving from a position where I'm expecting that my weights at some point going to convert to the right value that I'm trying to obtain. Okay, so this goes through epochs or different, let's say, cycle over your data set. One thing that is, and then, there is so-called performance, so the accuracy of the model that is evaluated using some way, an error or something that tells me how good is the output with respect to what I want. I mean, from the input, for instance. The value can be discrete, 0, 1, or can be, a number and a real number like probability or logarithm of the probability to make it larger in range. Unsupervised machine learning means the algorithms finds the underlying law by itself, doesn't need any help from outside. Yesterday we saw a possible example of unsupervised, for instance, the clustering. If you have peaks on a flat land, you have peaks and you say, this is something, different from the flat land. So I identify by myself, it's not necessary to tell the algorithm that you have a mountain. There is a mountain over a flat land, and it can find it automatically. Or you have a supervised machine learning algorithms that the opposite tell that there may be something that has a shape of a triangular. There's a real mountain, and then obviously you can easily find in the picture of a flat land at some point, a triangular shape. So there are different approaches, different ways. And reinforced learning, that is something that also allows to change over time the parameter of the system in a way that you don't need to continuously change the algorithm, because the algorithm in some sense is changing itself. The way the model in some way is changing over time, is learning from what it has around, and then try to make it better and better over time. Anyway, all these kind of algorithms can be, let's say the definition, the simplest definition of a machine learning algorithm is simply a transformation. You connect some variables as an input to some other variables as output. It's very simple. And the way how you connect can be that you are connecting, for instance, some real number to discrete number, like for instance, the classification problem, where I have different classes.
Let me see the other one. Can I try? Because probably it's just that.
It is, doesn't work. Oh, okay. Perfect. Much better. No, this is fine. This is fine. So classification, where you have, for instance, if I have to identify red dots from black triangles, features are, shapes, for instance. Another feature is the color. Another feature is the position. So I can for sure say that, this point here is different from the point that sits here. But for instance, one that sits in between the two classes, not so obvious to distinguish between one and the other. So, for instance, a typical classification problem in our field, in particle physics and nuclear physics, is to try to get out a signal out of a background. So you have, a background shape, and then you're trying to get out your signal, whatever it is. Or you have regression. Regression can be, for instance, an algorithm that take, in this case, connects a real number to real number, because you start from a set of data points and you end up with some numbers that correspond, to the parameters of this line. So you go from real to real. Every time that you can think in terms of, connection between an input and an output, this is a machine learning, or the equivalent of a machine learning algorithm. One of the particularly important, because neural nets are based mainly on that, is just a variation on that, is the linear regression. Linear regression is simply a linear connection between an input and an output. So, and the way how you connect it is through weights, so parameters in some way that connect to this relationship. And you have the performance in this case can be defined, as we know, if you are doing the fit of a line over a set of points, can be defined as we are used to see as the difference between the guessed value minus the one that you really have, or average over the state, and the square, because you want to have sum of positive numbers that gets to zero only if you can demonstrate if y hat is identical to y, then this quantity goes to zero. So the problem is that you want to simply minimize this function, changing w, so change automatically in turn you are changing y hat, and at the end of the day you find the best guess for y hat that keep this quantity equal to zero, or let's say close to zero, minimum possible. Okay? So this is exactly how we'll see how a neural network works. I mean, it's, again, no black magic. It's a very simple linear relationship. And if you want, there is also, an extra parameters, as we know in a line. There is also a so-called bias, a constant value that you add to parameters to the weights. So what you need to do is to change B and W using this idea that I want to keep MSE minimum or close to zero, in a way that W and B will be chosen to give me y hat identical to y when you average over the entire sample. Okay, this is something that we know very well as a physicist. It's not a big problem. This is one possibility of definition of loss function. This is exactly, you are minimizing, so you are trying to get the two things identical, but this is not the only possible definition you can think about. For instance, this is another definition with we'll see why we define something that not only take into account the error between let's say the guess, the value that you have and the real value squared and sum, but also try to get the W, that are the weights, as small as possible, because you see that this is the loss function. This is a function that needs to be minimized. So if this quantity gets larger, obviously you pay a price. Okay, so the system doesn't like and go back to another solution where this quantity gets smaller, because the goal is to minimize this function. Why we want to minimize W? We'll see later. But just keep in mind. And And lambda, in this case, that is a parameter that, is just in front of this, of the weight, is called, in this case, is what they call it, a hyperparameter. Okay, it's just weighting the weights, if you like. Hyperparameters are all the set of parameters that a machine learning algorithm has from outside, in some sense, so that you fix up front, but again, nobody and nothing is telling you that this hyperparameter is the correct one. You may change them, and obviously results will be different. Okay, so there are now methods that automatically scan the hyperparameter space, changing a little bit each hyperparameter in order to find, the best configuration. But again, you are not guaranteed that what you are finding is the best one. And also, another words that recurrent in the data in machine learning jargon is the regularization of the model. That this is a way to steer the model and to tell the machine learning algorithms, I want a W small. Again, just keep it for later, but this is what I want. And this is a way how you regularize your model, keeping, introducing this line. Again, this is nothing more, nothing less than just a feed of data. And then you can easily imagine that you can generalize the idea when points are not points. Point can be, image, can be dots of an image, can be pixel of an image, and then you try to compare the one that you have as an input with the one that you are trying to reproduce as an output. The way, obviously, that the one key point in all this business is you want to minimize the loss function, okay? So the loss function can be expressed as a multidimensional function that depends on the parameter and on your variable of your problem. Can be, complicated as much as you want, depending on the problem, depending on the model. And on top of that, the problem is that you don't know a priori the loss function, because this depends on parameters that are changing over time, and you change the parameter. So there is no knowledge of the which one is the real loss function that you end up with at the end of the training. It's living in a multidimensional space. It may have many multiple local minima that prevent it to go to the right, the final and the correct answer. We know very well, if you have a multidimensional function and you try to go down to find the minimum, it is not a trivial, not an obvious way, not an obvious, say, procedure. And the way how it is made is just, going down by gradient. So you calculate the derivative of each point of the curve, and then you follow where the derivative gets the largest value in order to find the minimum. This is, a standard way how you find the minimum of a function using, let's say, iteration. One parameter here is again, another hyperparameter in this optimization, this gradient descent is so-called the learning rate. Learning rate is something that you can see here. If the learning rate is very small, it means that your step looking, the minimum of this function goes forever, because you are doing too small steps. If you do the opposite, if you take a learning rate, so a step that is too big, you're going up and down, you never go to the minimum. So you have to find the right balance between the learning rate. So again, results may change significantly depending on the learning rate you are imposing. This is another hyperparameter of your machine learning algorithms. On top of that, you can imagine that this is not the only definition, that you go down in a, let's say, deterministic way, step by step, but you can, jump here and there in order to avoid that if you are going on a local minimum, you get stuck there. So you can sometimes, you jump out from that, and you randomly initialize or you move around in your function in order to find this minimum. Or you can also add some other, the moments of this function in order to, again, to avoid to get stuck in the local minimum. And this gives rise to one of the famous minimizer, optimizer, so-called, this is Adam. Just a variation on the algorithm. There's nothing, again, nothing particularly complicated or fancy. Okay, one thing that I was mentioning before is, fitting versus predicting. This is what we would like from a machine learning algorithm, is not only to reproduce what we have, but try to, be able to in some way to predict or to face situations that it was not trained for. Otherwise, we cannot say anything outside the training data set in principle. So there are, this is, again, this seems to be, trivial, but it is not. This is an information theory where you have, let's say, two different errors. So one that is related to the data and this is called the in-sample error, and the other is called the out-of-sample error, because you know the in-sample because you are training and you are reducing this error, but nothing guaranteed that the test set will have the same error. There is a theorem that tells you that if you go if the statistics is large enough, you at some point this E out is going to go the same as A in. So I mean there is a kind of convergence you are expecting if you are getting to a minimum, etc. At least let's say from the first principle, that it is possible. But pay attention, because we are just saying that the error gets minimized, so-called the variance. But it doesn't mean that your model is correct. You may have a bias. You may have a result that is not what you want. Okay? It's simply wrong. You are sure that there is a convergence, but you don't know exactly if you are converging to the right solution. Okay? And this is going to be a trade-off. We'll see in a while. In a practical example, that sometimes depends on how much you tolerate your error, or how much you want to have a bias. Larger is the model, so more expressive is the model, so more features, more parameters you have in the model, then obviously easier is to fix to fit everything. So in principle, you are reducing the bias. But at the same time, the error may get bigger because you are matching your solution to the training sample, and as we saw before, nothing guaranteed that when you go out from the numbers that you have, from the data point you have, you go to another data sample, you get a good result. Okay, so there is again a trade-off between the two things. So how big is your model? How many nodes your neural network has to have? Again, it's a complicated business, and there is no recipe a priori. Again, just based on the experience of the data scientists that design the architecture, or based on the trial that you do. You test it different and see which one that seems to you that is working better than the other. Like this is, a clear example. You have, let's say, two models. So the underlying law we know because we generate point according to a line or a polynomial of degree 10. Here is one and here is the other. Here is the training set and here is the test set. So you generate your events, and it follows perfectly. Obviously, when you try to fit your line with a polynomial of higher order, you get wrong. It's obvious because this was originally a polynomial order 10, and you're trying to fit with a line. Obviously, this is wrong and very similar. Maybe the polynomial gets better because you have more freedom in fitting it. When then you move to the test set and you ask yourself if is it possible to predict what happens outside the region where the model has been trained at 0, 1, and then you go from 1 to 1.25, so a little bit out of it. Without in this simple case, you get a very good prediction. So it means that your algorithm, in this case, minimization of the function, is working pretty well. What happens if I had some noise? Things are completely different, and don't forget that any measurements is intrinsically affected by noise or error. So you have your data are not aligned on as the underlying law is expecting. They have the underlying law plus some other effect like noise. And in this case, if you do that, the same for the training set with the linear shape or with polynomial and try to extrapolate outside, you see that in this case, the extrapolation with a simple line is much netter than you can do when the underlying law was more complicated. So showing that, a simple model can in principle be works better than a complicated, like in this case, multi-polynomial, multi-degree polynomial model. You can, get rid of that if you increase the statistics. You have a lot of data, and then you may have a better, reproduction even in the complicated case. But still, when you go out of the region that you are trained with, you train very well between 0 and 1, because now the statistics is huge. But when you go out, still your polynomial in the order 10 doesn't get the right shape. Again, this is to demonstrate that there is, a trade-off between the bias and the variance. So how complicated is your model? How depends how many data you have, what is the statistics you're using for training, what is the statistics of your data set. That is all parameters that enters at the end in the quality of your machine learning algorithm. And on a side note on that, that is, in some way, again, connected to that is, for instance, can AI help or support the capability of get rid of detector effects? We are, at least experimentalists measure something, but every measurement you do is affected by some smithing, some resolution, because within a certain values, even if the resolution is very good, anyway, you have an error on whatever measurements you are doing. So the question, and this is one of the two effects that the detector introduces. The other effect is related to the acceptance, because when you measure something, you will never measure the entire phase space. You're not measuring all points in the phase space. You are always sampling the data that you have in a limited part of the phase space. Right? It's reported here. I can, combine different measurements in different areas, but it's very unlikely that you really cover all possibilities, all the phase space available for that measurement. So why for this meeting? In principle, this can be done. AI can help in trying to get rid of this meeting. If you train the system and the machine learning algorithms, you have to teach him, you have to train him with what's the effect of, you have a proxy for your detector, okay? So the algorithms understand what happens when a data gets in your detector and how it gets out. So makes a connection between the two, and in principle is able to unfold to say, okay, I see a particle moving at 1 centimeter, but I know that my detector, when I measure 1, means originally that my particle was at 0. So I know, and I put, my smart algorithms put back the value to 0. So this can be done, and actually we demonstrated even in a complicated case that this is possible. I mean, you are able to learn even a complicated, a realistic resolution. This is not Gaussian resolution. This is a real resolution provided by a complicated correlations of detector performance parameterized through a giant proxy of your detector. That obviously is not reality, it's anyway a proxy, but for sure is not only giving, just a Gaussian spread. And this works, you can do that. Acceptance is much more complicated because this goes again in the philosophical problem of where, if I measure here and here, what is guarantee me that I know what happens in between? There is no, clear way. If you train or if you are supervising using the PDF, the probability density function, that in our case is a cross section, is a distribution in the space of your events that are distributed. You are measuring these events, and then you are trying to understand if you can recover the area that you are not measuring. But unfortunately, this is not possible. Again, this is logically impossible. It's not. There are other tricks that you can play, like imposing the characteristics of your, if you know, or if you think that is the function that describe the basic elements of your process are under control. They have some properties. You can inject this property, like for instance, you can constrain using the parity conservation, analyticity, or unitarity for this function. But the problem is that the cross-section, so the probability of having a particle going in a certain direction, is related to the square, as we listened this morning from the other lecture, is the sum of square of amplitudes. And each amplitude is the sum of all possible processes that a particle can undergo. So it's clear that you are supervising on this quantity and you are imposing condition on this amplitude. So it's not obvious that you are able to really constrain the system to go where you want, to be sure that it's under control. So again, this is just to tell you that fitting is not the same. Even if I have, an infinitive statistics in this area, nothing guaranteed that I am doing right in extrapolating in the area that I'm not measuring. Okay. Now let's move now to neural networks. That is going to be one possible incarnation of AI algorithms. This is not the only possibility, but they are widely used now. Actually, they are back in the 80s. They were not used simply because you need to have a lot of computing power to make some sense of it. I remember when I was young, I was probably second, third year at university. They call it adaptive system. They didn't even call a neural network, but it was exactly the same thing. You have, kind of weights and you could in principle describe, you have a transfer function that connect an input to an output with some weight in between. And we were doing, by hand, this minimization that now is done numerically, it was done analytically, defining the function and trying to calculate derivative. I mean, it was obviously a mess and very limited application. So now it works because you can do that, automatically, or you can do that by brute force using computers. On top of that, you have now a lot of libraries that already implemented all what I say. You will see tomorrow that implementation and building a neural net is just a matter of combining, bricks, and each brick they say, I want to optimize our Adam, and you just write it, and that's it. Or you don't really need even to know how Adam works. It's just, you call it and that's it. It's the function that is provided to you. So there are, many libraries that makes this approach very easy to even for people that do not have, the full understanding or expertise in what they are doing. Neural network has, the basic ingredients is what's called neuron. Again, this is a linear regression. We saw it before, but now the trick is to combine many of them that has an input. You're setting different inputs. So in principle, you have different variables that are combined together through weights that are linearly connecting the output to the input plus a bias, exactly as we said before. To give more freedom and more capability, you add up what is called the activation function. That is, you multiply this output by a function that usually is not non-linear. Can be, again, here there are many different activation functions. They can be, going to zero, they are smooth, or they go up, they go to zero, and they depends on the weight. So you can have, the problem is that this activation function can be very difficult to derive. I mean, at the end of the day, remember that what you want to do is make a derivative of your function, whatever, linear combination is easy, but as soon as you put a non-linear part, it becomes more and more complicated. And again, only thanks to the capability we have with computing power, we can do, this derivative very easy, but imagine if you have to do that by hand is almost impossible. And then the trick here is to put together different neurons. So the output of these neurons is propagated to a second layer where you have other neurons that makes, the mix the output of them and go forward to a next level, putting again and again different layers. This is one possibility. You may also have, other kind of connection between neurons. This is the simplest and let's say the more logical way that you can think about for a neural network. Again, it's not the only possibility. So you have activation function that you can choose from. And this is, again, when you put all together, you make your big loss that is going to be function of what? Weights and input, and then the variables that are connected together. Okay, you define the square, the minimum square error exactly as we said before. You put all together and you try to minimize. This is exactly the same as we were discussing before. Sometimes, the problem is that when you introduce this function, again, you may have that they are not, or it's very difficult to make the derivative. Or even worse, if you see you have a function that is flat, that kills completely your output, and so there is no derivative. So you remain almost in a flatland. You want to go to the minimum. So this is the reason why nowadays you prefer to use a function like ReLU is one that is different from 0 as a function of weight, but you see it's going to explode. When weights are big, this function gets bigger. And so you multiply by a number bigger and bigger and bigger, and that's, you want to minimize something. This is not the right way to do. This is the reason why you put a value that kills the weight, try to squeeze the weight to lower value. So it's bringing back even if you use this function, you can go back to values of the weights that doesn't explode and then do not converge, the network. Okay, so this is the reason why I was mentioning before that you want to weight your loss function not only with weights but also a term that is proportional to the size of these weights, and you want to keep the weights small. Okay, so this is the reason why ReLU function as an activation function is the one that we use now. But I mean, in the past it was very difficult to make derivative of that, while in principle, the hyperbolic tangent or a sigmoid is much easier because they are, analytic function that you can define in an easier way. So how a neural network works in practice? You choose the neural network architecture, so define which one you want to use it. Define your loss function as a function of, the variables, can be strictly the SME, or can be, a combination, can be part SME plus other stuff. I mean, it depends on what you want to do. You regularize the model. That means that you try to minimize the unwanted connections of the neurons. You prepare the data set and then train the network and check the results on the test set. And, you have fun. This is the way how it works. This way, obviously, this approach is much more powerful than the simple regression, linear regression, because it's putting together is, first of all, non-linear, because there is the activation function, it's putting together many inputs. And also there is a theorem, again, that is a theorem, so it's well established, that tells you that a neural network with a single hidden layer can approximate any continuous multi-input, multi-output function with arbitrary accuracy. That means that in principle, you have a filter of whatever function you can imagine, whatever relationship you have between an input and output, you can mimic, you can reproduce it just in enough ways. Okay, this is just probably something that, again, if you think about it, if your polynomial gets higher and higher in degree, you can almost fit any shape that you start from. Okay, this is just, again, not the demonstration, but is the base to use neural network. In principle, you are at least in principle, that this can resolve every problem, can converge to the right solution. Maybe you are not in the right solution, but one solution exists. That is already something. Again, if you have a hidden layer, I forgot to say that you have this external layer, we have an input and output, and what remains inside is called hidden layers because you don't have access. They are not correlating input and output. You have something in between that in principle you can totally ignore it. And adding obviously more layer gives you more expressivity to the network, so you have more freedom. But remember that the more weights and more complicated is your network, easier is the fact that you can overtrain if you don't have enough statistics to train your network. So again, this is the balance between the bias and the variance in your network. And again, the way, which architecture you want to choose, again, it's absolutely not predefined. You may find for a problem many different networks that work, or many different networks that do not work. It's a priori, it's not clear which one is better than another. And then there are, variation that put together, for instance, the neurons in this case are not only connected to all neurons connected to all nodes, but you have some of them that are only connected to some of them. It's a limited connection. Or you may have this is the structure of the encoder that we'll see more in details later. So you go from an input to a middle layer that is smaller in size, and then you go back in the larger one. Or you may have this GANs, the generative adversarial network, that is the example I'm bringing now, just to give you a sense, a feeling of what you can do with this kind of technology. That is, it was the state of the art up to probably a couple of years ago. Because it's very difficult to train. It's very easy to not find, the minimum. Again, you have to be quite expert to use this. But if it works, it's very, very powerful. And actually, we use it to in the example I'm going to show you in a while. The idea of the neural net is based on the backward propagation, where I start with a certain values for my weight, I calculate the loss function, and then I check if it is good or bad, and then I go back and I change the value of the weight, go back to the loss function and check if the new step is better than the previous. If it is the difference between what I'm training with and what is my output gets smaller, means that I'm going to go down to the minimum. If it is bigger, I have to go in the other direction. Then I change suddenly rapidly my weights. This is the idea. Okay, so you go back and then change. This is the reason why when you train your network, you need to go many times, many epochs through your data set, because the first and every time you start from a configuration of your weights that is different. So every time that you go through it, you are not starting from scratch. You're not starting from the same condition. You start from a different condition. Okay. And on top of that, you can, again, regularize your network. I'm reporting that because in the example with the autoencoder, we have the pruning in some way is getting rid of some of these low weights or weights that are close to zero. You say, why I have to go with 0.0001? I can just drop it. Probably it's not going to change much in the architecture. We'll see how much it's affecting when you drop out and when you prune it. And you reduce the number of weights. This can be, relevant in particular if you run the place where you put this weight is small. I mean, it's not very big, and then you need to have a limited number of weights. Just let me go through a problem that is, closer, let's say, to the field, or what you can probably understand easily. The idea of the cross-section, if you think about this, is the kind of AI algorithm is exactly the same, because you have, your data set, you run an experiment, you take 1 million events, then you collapse your 1 million events in a single function. Okay, because you know that the structure of your function that describes the cross-section of an interaction is based on, this formula. So you are putting together the amplitude. The probability is calculated as the square of the transition amplitude. Okay, we know that. This is well established, and so this is the reason why I can, at the end of the day, even if I have 1 million events distributed in space, I can, at the end of the day, get a single function that describes pretty well my data set. And this is if you think about it, is a very compact way to conserve and to preserve the original information. That is how the scattering amplitudes are. Now, this works absolutely very well if you are in 1D or in 2 dimension, and people use it. That is the photo production of omega. You see, you have, you take your data and then you describe with the cross section, and this is results of taking, millions and millions of scattering omega produced by photons hitting a target, a proton target, and producing an omega particle in the final state. And at the end of the day, you end up, this is the final information, the final condensed information that you want. This works so why, I mean, in principle, you don't need AI to do that. It's already very well said. And, I don't think you can do better than that. The problem is that as soon as you go not to two particles to two particles, but simply 2 to 3 particles, so just adding a particle in the final state, the number of variables that you get that depends on the momenta of particles that you are producing gets, from 1 or 2 goes to 5. So you have a problem in 5 dimensions now. That is even difficult to, not only to understand if you are doing right or wrong. The problem is that you can even visualize it because it's 5 dimension. We cannot master 5 dimensions. So you need to project it in 1 or 2 dimensions at most. But when you project it, all the correlation that you have in the multidimensional space that are embedding the physics of the process gets lost. They are lost because you are projecting. So you are integrating, you are averaging, and so lost. You see, this is an example, for instance, this is a spectrum of 2 pion, photoproduction of the 2 pions, where you have resonances. Each of these, density is representing a process, is representing, in this case, production of a particle. So obviously, the information you want to preserve, you want to study, this is exactly what you want. Understanding how these spectra are correlated in order to extract what are the basic, the underlying law, in this case, resonance production as an intermediate state that decay at the end in the 2 pions of the final state. So you see that if I take, the full picture, b-dimensional, it is already a reduction because the original cross-section is a 5 dimension. Anyway, let's say the 2 dimension is better than 1. And then if I project it in 1, you lose. You don't know what's going on here. While if I see the plot in 2 dimension, I can clearly see that there are, 2 different processes. In this case, you have a pion and pion that resonate to give me a rho. In this case, on the opposite side, you have here this band that corresponds to a proton and a pion that give me a delta, an excited baryon. Okay, so it's clear that in the 2D, I can, disentangle, I can at least understand that there are 2 processes. If I project in 1, how could you say, if I look at these variables, that there is a peak here? I need to go on the other projection. Okay, if I project it, you can imagine if I project it is a b-dimensional plot on this axis, you will see a prominent peak corresponding to the rock, and then a smooth background coming from a peak in the other one. Or if I choose the wrong variable, in this case is the proton pi plus and the p pi minus, where there is no delta plus plus, where there is no rho, or a combination of them, the rho totally disappear because it's hidden in the projection. This is just the geometry. It's nothing again very complicated. Just to show you that even just going from 2 particles to 3 particles is almost impossible, or you have to have very, very well defined method to extract this information. And then we try with GANs, and the idea, the GANs is just coupling 2 different networks, one that generate your image, the other that make a comparison between the image you have and the training images, and you go back with the back propagation to say, no, I see here, let's say a cat, I'm generating a dog, so no, it doesn't work. Let's go back and change the generator weights in order to adjust and get, a cat in place of a dog. And the same thing, if you think about it, is very similar to what we have. You have in nature, your distribution of particle in the space. You have a generator that generates all possibilities, all possible phase space compatible with that reaction, and you compare, and the discriminator at some point is cannot distinguish between what is the training set and the generated let's say fake images, or in this case particles in the final state, and you have the hope that your generator, you detach this part and you have a generator that generates exactly the physics that you are that you train with the network. This was the idea. There is a complication, again, the detector in between. You are not really measuring what the original cross-section. You are measuring particles that are affected by distortion induced by the detector. So you have to remove them. And so this is the reason why you need to have something, another network, so another GAN that acts like a proxy of the detector, that knows what happens when a particle enters the detector. And again, this is not trivial because you are using a model, you are using GAN to parameterize your detector. It doesn't mean that you are pinning down exactly the characteristics of your detector, but this is what the best we can do. You have a model of your detector and you use it to mimic the behavior of your detector. And you can have then a neural network, you have a GAN that mimic the behavior of your GAN program. And you inject here, so at the end of the day, you have a generator that generates events at vertex level, so as they should be, and then go through the proxy of the detector that gets distorted. This was pre-trained, so he knows how the detector acts on the vertex level particles. Make a comparison with the training set, and again, back propagation, train the whole system, and if it works, at the end of the day, you get a generator that generates events at vertex level. So you get rid of this spread due to the detector. Okay, this is all obviously only true if I look at within the acceptance of the detector. So this needs to be all the machinery, all this idea works, because if I go outside, I'm not guaranteed that the network, because I have nothing to train with, because this is zero. I cannot compare to anything because I'm not measuring outside. So how could the machine learning knows what happens outside? And actually, this works. I mean, we apply to even to these 2 ions. You see that it's very complicated behavior in the 5 dimension. We apply to that, and we got a comparison. These are generated events after the training with real data. This was a closure test, so we generate data, pseudo data. Let's say go through all the chains, so we could compare the ground truth with what at the end of the whole process the network was generating. And as you can see here, the comparison is very good. I mean, we were able mainly to mimic, to understand what we generated. We were able to extract in some sense what we did. So this was, a successful demonstration that you can unfold the detector effect, and you have, a generative way to reproduce your data. So this is a very powerful, let's say, application of AI. Tomorrow we are going to talk about an autoencoder. Not GANs are too complicated. Again, they are very sophisticated. So let's start with something much easier. Autoencoder is usually, one of the simplest neural net you can imagine. And the autoencoder is, just again, quite simple. The idea is quite simple. You have an input. You encode the information contained in the input in the what they call latent features. And then you have another part of the network that start from these numbers and get the original picture you have. So there is no, compression is the Liouville theorem in the information theory. There is no actually, you are not, the information you start with is in part distributed over the encoder, the decoder, and the latent space. This is the reason why you can get a compression. You can, if you want to have in some sense, these numbers is coded in the 3 pieces. It's not only, I start here from an input that can be, complicated as you like, and then I go to a smaller space of features. So let's say that I have here, we'll see at the end a picture that contains, 700 pixels, and I can go here to, let's say, 10 numbers where everything is encoded. And then from these 10 numbers, I can reconstruct my 700 pixels. But the trick is that part of the information goes into weights of the encoder and decoder. And the idea is that these weights are always the same, so you don't need to change it. The only thing that, are representative of this number are the features in the latent space. This is the reason why you can use an autoencoder as a compressor, because the information gets shrink in a smaller volume and then gets enlarged again when you use the decoder part of your compression. The way it works is exactly the same as before. It's always the same. You have a function that in this case again has lambda multiplied by the weights, and you want to minimize a loss function that is defined as the difference between the input and the output image. You take your data set, you split in a training part, you use the test part, you use the validation part during the training, and then you play the whole trick. There are many different kinds of autoencoder. This is the simplest you can think about. It is a feed-forward autoencoder that has a structure with the same layer, number of layers here, same number of layers here, is symmetric with respect to the encoder and the decoder. So I go from here to here and then from here to there. Okay? With two transformations, as we said. A machine learning algorithm is nothing that connecting this set of numbers to the input and then connect it to this set of numbers to the output. Okay. One thing that specific for the encoders is that you usually want to keep the information in the latent space as a part of the output. You are not only after getting something that I feed into a number 2 and I get a number 2 at the end. I want also to use the information embedded in the latent space. And there are reasons to do that. Think about, for instance, a catalog. You have your phone book with thousands of numbers, and you are looking for a specific number. Now, you have to read the entire line. If I can compact my catalog, just taking, going in a space where each line gets shrinked to, a smaller size, I can go much, much faster over the entire catalog. So this can be an application of the autoencoder. Or you can simply compress your data. Actually, there are algorithms that use autoencoder to compress music, for instance, without, losing like MP3 or algorithms like that. In principle, you can use them to reduce the size, because you have the coding part, you have the decoding part, and what you are keeping is just the central part, I mean, the numbers in the latent space. Or you can have, for instance, anomaly detection. This is another way to use an autoencoder. Now, I train my autoencoder to identify numbers 1, 2, 3, 4, and then the way how I can identify 1, 2, 3, 4 is always, very good. At some point, I put a 7. 7 is different from the rest. So autoencoder tells me, no, there is something wrong. It is not 1, 2, 3, or 4. It's something that I never saw it. And then you can identify an anomaly, something that, is not the correct one. Or you can use the denoising. The denoising means that you start from a number like that, you put some, spread in your pixels, and you can sharp the image because it knows that, when you train it, you test that is 2. So you want to get out a 2. So every time that you see something like that, you say, no, this is not, just a random pixel. This is a real number 2. So I mean, there are many applications for this autoencoder. And the way you usually make it, again, you have an activation function. You can define a loss function. You have to choose how many layers you want to have, how many neurons you have per each layer. So this is the kind of freedom that you have in defining the network. And here are some results of this autoencoder. For instance, goal of this exercise is to compress the image to latent space and decompress it. Okay, so each image is 28 by 28 pixels, so it's 784 features. That each pixel has a different value. Okay, and 0 means white, 256 means black, and all in between. So you have 784 numbers to feed in per each image. You feed it with a lot of them, and train the system to identify the numbers. And depending on the, for instance, this autoencoder was built with, obviously you need to have a 748 input because each pixel needs to go to one neuron. So at least you have 748 at the beginning, you have 748 at the end, and the simplest, the simplest architecture is put a hidden layer in between. Doesn't mean that you can put multiple layers in between. This is the simplest you can imagine. And they make, the comparison when you have a latent phase that moves from 784 to 8, or 784 to 16 or to 64. And you see that even 784 to 64 is enough to reconstruct pretty well the numbers. If your goal is to identify numbers, it's probably, you don't need to bring the entire 784 pixel. You just need to know these 64 numbers, and you immediately can identify if it was 1, 2, 3, 4, the other figure. Okay, and again, this was trained using Adam optimizer. The loss function was compared. This is a different definition, MNCE or crossed entropy, another way, to binary crossed entropy is another way to define your loss function. And you see that, for instance, it's quite independent. I mean, the algorithms work to whatever loss function you are using. It's pretty robust with respect to the choice of the loss function. And also the denoising works pretty well. This is a noisy tool that gets, for the standard architecture, gets, nice, but if you then use an auto encoder with convolutional layers is a little bit more complicated. You get very, very good results. So again, this is the base of many of the system used also in cameras. So when you take a picture to the noise from the pixel, there is a thermal noise due to the silicon, and you can get rid of it using this kind of algorithms that just the basic idea is that you are summing up a signal that is a signal with something that is completely, let's say, white noise. It's randomly distributed. Obviously, if you have a little dot of dust in your camera, I mean, this doesn't work because it identifies the spot as a good one, like part of the image. So the trick again is the unsaid is that you are expecting that the noise is going to be add up randomly to your image if you want to get it out from this algorithm. And that's it. So for I think that this is more or less, I hope to you are still alive, you didn't fall asleep. And tomorrow we'll see application of this autoencoder to our specific problem of compacting. And we are going to use it all, we'll see that the Keras library is using, call it Adam optimizer, calling, how many layers we want to have for the autoencoder, how many nodes you want per each layer, etc. Exactly the same thing that we discussed today in practice, how, it works, how you can code it by yourself. Thank you.
I have probably a naive question, but I don't understand what is the advantage of using machine learning for encoding or decoding when, I mean, essentially this problem is like encoding, you find a function that reduces the space from RD says to R n where n is less than D. And then you basically apply the inverse function to get the original resuls.
But this is the point of the encoder, that you can stop in between and say, I have my pulse, that is something that goes in this way, is an exponential, okay? If I fit it, I can, this is a e to the minus t. So I can, with the alpha, let's say b, with the parameter. Okay, I fit it and I encode the information of my exponential in two pieces. One is parameter a and b. So a, I know a and b, and I have to know that the function f is equal to e minus a is made in this way. This is, let's say, the way how you combine these are A and B are weights, the equivalent of weights in this machine learning language. And the function is exactly the same. I mean, this combination is the encoded part. So the latent space tells me that A is equal 5 and B is equal minus plus 10. So I can code, this complicated shape that a priori is not, is not only two parameters. I know these two parameters because I know there is an exponential. So I'm adding this information in this part here. And this is what when you have the network that goes, from a certain number of inputs to the latent space, here there are all the weights. And the weights is telling me that this is mimicking A multiplied by E minus B T. So at the end, here I got A and B. The function is this part. Parameters is here. And if you know that, and now if I want to build my function where I started from, I just do the opposite. I say, okay, I have A and B. So I know that my function is generated by E minus B this way. So the decoder, in some way, the weights of the decoder knows how the function is, and then I can rebuild up any state. There's nothing more than that. You are encoding your information.
This I understand. I'm just saying that if you know the function, they're easy. It's just a reduction, then you just apply the inverse. If you already know that that's going to be an exponential, or you can have I don't know, you decide that every time I use that function, it's fine. But I guess this is the machine learning is finding whatever function.
Exactly.
No.
This is the point.
Is that the advantage?
Yes.
Because I wasn't sure.
Yes, absolutely. This is the point that as you mentioned already, that in principle, a layer, an hidden layer can mimic any kind of function, any kind of relationship between your input and the output. This is guaranteed. Again, it's not guaranteed that you are converged to the right solution, but you're guaranteed that a solution exists. So you have, it's not that if I know that it was an exponential, I don't need to use machine learning. I got it. In case we see tomorrow, we are going to have a more realistic function that goes, in this way. And then, how to deal with that. Okay, I can parameterize like a line and an exponential. So at the end, it's probably, two parameters here and other two parameters here. So I can probably imagine that, with few parameters, I will be able to my autoencoder. If I have signals that are all in this way, the compression ratio is huge because in our case, for this signal, imagine that the features you are feeding to the encoder is point by point. So you are sampling and you have, 50 points and you move from 50 to 2. I feed in 50 points and I get only 2. And then from the 2, I can get back my 50 points. Okay, so the compression is huge. If you have a more complicated structure, the compression obviously is you have to have more freedom. That means you have to have a larger latent space to code the information that you start with. But I think the advantage is that when I am in this latent space, I can use the information here. I forget about my 50 points. I just consider the 2. So if I have to go through, scan a list, if all my shapes are coded in 2 numbers rather than 50, this is much easier than to go through if I have, 1 billion numbers, rather than going, through one by one and check if, I know that they already, they are all compressed in the same way. But there is no magic. You're, absolutely right. If I know that it's an exponential, why I have to, spend time? I fit it and that's it, and it's easier. But, if you have your function that maybe over your 50 points is not always in the same position, sometimes, can be here. Sometimes you may have the pulse here that, make your fit. If you ever fit a function, your experimental data or whatever, that, it's not you have your macro that goes through all, let's say, 100 histograms that are expected to have all more or less the same shape. But 99 it gets good and one fail because the peak was a little bit skew and the function was not initialized in the right way. This happened all the time when you do a feed. Machine learning, in some sense, is more robust. It's give you a way that is automatically adapted to the conditions. But there is no black magic. It's exactly the same as you can do. At least what I try to convey that AI is not really something magic. It's not magic. It's something that may be more flexible, maybe. And sometimes, again, if I have to write a catalog of 1 million of these shapes, I can compact it in a very small size. So it's useful. Why not?
So it's somewhat like cryptography, right? Where if you know the secret or the latent representation, you need to know something about the encoder and how that was built before you can build the decoder.
Yeah, this can be another application. Yes, if you know the two pieces, you know how you are encoding the information. Then only if you know let's say the decoder part, you can.
Yeah. So you need both the secret and the key.
Exactly. Yes, exactly. Is the basis for that.
Sorry, I apologize if this is weird, but in principle, you can use this to replace your simulation detectors, right? And then in that case, all you have to do is just dial in some input parameters because you've already trained, and then just recalculate this back.
Yeah,
which would speed things up for you in principle.
I mean, black box. Okay, you have an input. You're going to extreme of this idea can let's say do the reconstruction not based now in any experiment. As we see, Rose before was talking about different detectors, how you get information out of all of them, and you are not going a level of electrical signal. You usually have a partial reconstruction of each detector. Then you combine to give you at the end of the day your form momentum of the particle. Form momentum means that you know which particle is it, particle identification, you know the momentum, and you know everything about the particle. Okay, position and all the rest. But in principle, I mean, nothing prevented to say here I have my voltage for my detector, VI, for my my array of different signal, and here I have my form momentum. So this is what the detector, in some sense, the reconstruction does. So if I know this transfer function, I can just, every time that I have a combination of these numbers, I know that this corresponds to a particle going in a certain direction with a certain momentum in a certain position. So yes, and how you do that? You have a giant simulation of your detector. You feed in this case, the particle. You know that the way you train it is you have a generator again. You generate your particle. Here is your neural net, let's say the discriminator. You feed in what happens when you have a generated event. I know the effect of the detector because I put here the reconstructed, okay? Because here in between there is the detector. And then this, I can teach this block here to behave like the detector. I train, I know what I generated, I know how it transformed by Giant in something that is equivalent to what I measure, so I know the connection between what I see and what it was. And then I can use it. In principle, yes, it's, in principle, a neural network can make a radio, can make a television, can make everything. It's flexible enough to reproduce whatever. This case is reproducing the detector behavior. And it works. I mean, because one thing is to say, okay, in principle, it can work. We demonstrated that even we use the detector like class Jefferson Lab that was a very, very ugly acceptance. So it's cutting here and there with a very ununiform acceptance. So it's really a stress test for the system because it's not obvious at all to reconstruct it. It's not that I have my particle at most that they are reduced because I'm not measuring all of them and I'm measuring 90% of them. No, they are chopped in the phase space. There are strong cuts because the acceptance is weird. And we demonstrated that we were able to do a closure test where we know exactly what we generated within the acceptance of the detector. We were able to get back what we generated at the end of this loop.
For the models that you use in your research, do you have a favorite method for choosing the hyperparameters, maybe like a hyperoptimization libraries?
I cannot tell you. I don't know. No.
But is it all just kind of trial and error?
I think that at least that is what my guys, the expert in data science, they have a lot of experience and they know immediately which one is more suitable for that specific problem. It's really based on experience. It's not. I don't think that there is any general. There are some automatic way now. Part of the libraries also include scans over the hyperparameters in order to be. But the final test is just run with parameter 1, run with parameter 2, run with parameter 3, and compare results, and then decide which one is working better. This is for sure. I mean, there are no receipt to be sure that one is better than the other. You just have to see what the result is. Because, the parameters and the way, if you think about it, if I have, 1 million weights, when you train twice, one trick that people use to use the same training, I mean, one thing that I didn't mention is about the systematic error associated to this method. I run my gun or whatever, I generate my events that are pretty nice, very good around my points. Then I use another training set and obviously I get the different results. It's not exactly the same, it's different. So you can generate this multiple sample, not changing the data set, but just changing the position of the data within the data set. This is called replacement. Because the weight, when you go through the data, gets changed based on the sequence of points that you are training with. So if I change the sequence, how the weight changes is different. And you can really see it. If I change, the retrain with exactly the same number, 1, 2, 3, 4, now I train with 1, 4, 3, 2, results is not the same. Because the weights gets different. And then if I go through my set of data, once, 1, 2, 3, 4, the second time, 2, 3, 4, 1, then 3, 4, 1, 2, etc. I can have 4 different samples that I can use to train, even if they are statistically, the same thing. But machine learning doesn't know that they are the same. Actually, they are not for the sake of machine learning, because it goes through, every time that goes through these 4 numbers, the way how, even if you start from the same condition, I choose my set of weights at the beginning, 0, 0, 0, 0, go through my first block of data, and then I repeat it, and obviously it gets a different value, because weights, the combination of weights is different every time. So, it's really, this is the reason, again, why you have to be very, very, very careful in managing, also quoting results out of the machine learning algorithms, because can be, easily contradicted by running exactly the same condition, changing a little bit in your procedure, you get completely different results. Not completely, but you may have different results. So this is the reason why systematic error and again, uncertainty quantification now for us as a physicist is very important, because whatever algorithm you are using, then you want to quantify what is the output, and you want to be sure that it can be reproduced, for instance. That again is not with this, because it's a very complicated nonlinear problem. And you know that the propagation in nonlinear problems is the butterfly effect. You know, you get a little difference in the initial condition gets, amplified again in a totally completely different state. It is more or less the same thing. You have a complicated, the neural network we were using to fit our stuff was about millions of parameters. So, there is no control at all. I mean, you cross your fingers and test different and then check and quote the bands that you get every time that you change a single detail in your network as a systematic error associated to the procedure. It's a different way, very different way of thinking in the standard analysis where, at least the statistics is well known, maybe simply because people know from hundreds of years, so they know how to deal, how to combine Gaussian errors, In this case, it's much, much more tricky.
Yeah, tired. Once again.
Quick questions. I found one driver. Are there any other drivers for tomorrow? Anyone else have a car? Okay. And then